So to wrap this lesson up, we're going to talk about some of the questions that you had throughout the activity, just to make sure that you understand what we're going for here. And one of the first questions was this one. In multiplication, does it matter in which step the simplifying is done and why? So here is an example of a multiplication problem that you did in the lesson, and you were asked to simplify it in this step here. So we multiply the top and the bottom together, we get this. And we notice that it has an x minus 2 term in the top and the bottom. So we were able to simplify it down to this. Now, if you notice, though, this x minus 2, actually, you can see it right here. So could we have gotten rid of that first? And the answer is yes. You can actually cancel those out up here instead of multiplying them together and then canceling them out. And that's because the order of operations, if you remember PEMDAS, so parentheses, then we do exponents, then we do multiplication and division. You maybe weren't told this, but multiplication and division are actually on the same level, and so is adding and subtracting. So if you have multiplication and division, which canceling these out is basically an act of division, and multiplication and division are on the same level. So you can actually do them in any order you want with each other. So we can divide out those factors first and then go on and multiply. And sometimes that saves us some work. So it doesn't matter in which step the simplifying is done. The answer is no, because of the order of operations, multiplication and division being on the same level. Our next question, how could you check your answer after performing an operation on a pair of rational expressions? So this is a very important question because sometimes you'll get an answer and you may not feel comfortable that it's right. I mean, there's a lot of places where we could make mistakes, and it's just nice to be able to have a way of checking to reassure ourselves that we did everything correctly. So here is an example. We started with this, and we ended up with two versions of our answers. We're actually going to check both of those and make sure they're both correct. But how do we check them? Well, one easy way is to graph the original and to graph your answer and see if they give you the same graph. Because if they are the same, the graph should be the same. So here I went ahead and graphed this top equation here, and I got this. And then I graphed this here, and I got this. And you can see they are the same. This is obviously easier to do when they're on the same graphing screen, but you can see that they are in fact equal. So that means that these two things are equivalent expressions. All right, our next question has to do with addition. And here's the problem we're going to look at while we talk about this. It says, after writing both terms with a common denominator, are they equivalent to the original terms? So in this step right here, where we got the common denominators, they're asking, are these terms here the same as these terms here, or did we change what we're doing? And the answer is they are the same. So what we did to get this to look like this is we just multiplied it by x minus 4 over x minus 4. Well, that's just basically multiplying by 1. And when you multiply by 1, nothing changes. So this is exactly equal to this. It just looks different. Same thing over here. We multiply by x plus 7 over x plus 7. That is also equal to 1. And so this is equal to that because we just times it by 1 to get to that. So this problem may look different on this step, but it really is the exact same problem. We've just resolved the issue of not having the denominators the same by multiplying by a clever form of 1 to get them to be the same denominators. And then from there, we can just add the tops. Our next question asks, is it possible to get an answer in an addition problem that still needs to be reduced? And if so, how can you tell that your answer needs to be simplified further? So we're going to look at this problem. We added these two things and ended up with this solution down here. Can we reduce anything else? Well, that would only happen if the top factored to have something that either had an x plus 3 as a factor or an x minus 2 as a factor. And so, yeah, it's possible that you might have something else that needs to be factored out. But the only way you're going to know that is if you are able to factor this out and see if it has common factors with the denominator. And something to keep in mind is it's only going to be able to cancel with one of these things on the bottom. So really, I only have to see if this polynomial on the top has either of these things as a factor. And if it doesn't, then there's not going to be anything that cancels anyway, even if it is able to be factored. So when you get to the last step on an addition problem, just check to see if one of these things can be a factor. Here's an example of how you would do that real quick. So I'm asking, can 3x squared plus x plus 21 end up equaling something like x plus 3 times something? And if we think about it, to get the 3x squared, timesing your x, you'd have to get a 3x over here so that you get that 3x squared. And to get the 21, this would have to be a 7, so that 3 times 7 equals 21. And now let's see what happens with the middle terms. So you would have 3x times 3, which is 9x. And then you have x times 7, which is 7x. And when you add those together, you're going to get 16x, which is definitely not equal to plus 1x. So this thing is not going to factor as x plus 3 times something, because the only thing that would work to get the ends won't help you get the middle. And so I don't really have to actually factor it. I just have to realize that this is not a factor, and so it's not going to cancel. Now this one might be a factor. I would still need to check that, but after seeing that that one isn't a factor, then I would know that there isn't anything left to factor. And if it does turn out that either of these are factors that are shared by the numerator, then we just cancel them out and simplify the fraction down like we've always done. But you should remember to check. And our last question has to do with subtracting. There's often sign errors that are made when people try to subtract rational functions, really any subtraction we need to be careful with. So what are some strategies that we can use to make sure we don't commit those errors? So here's a subtraction problem from the assignment. And really this step is the one where we have to be careful, where we actually do the subtracting. And there's a couple different strategies that can help you not make mistakes. One is to maybe line things up. So you could take your numerator here and write this as 3x squared minus 6x plus x minus 2. And then we're going to be subtracting from that x squared, a minus 4x, a 5x, and a minus 20. And so when I do my subtraction here, now everything's lined up with things that are like terms. So I could do 3x squared minus x squared is 2x squared, and so on. Okay. Another tip that helps students a lot is to add the opposite. So we're subtracting right now, but if I change this to an addition sign and change everybody's signs inside, adding the opposites of these will end up being the same as subtracting what they were originally. So 3x squared plus a negative x squared is a 2x squared. And you see that's what we did here when we rewrote it, is we added the opposite. Another thing you could do if you don't want to line them up like this is you can just keep track by marking off the ones that you have added. So once you've done 3x squared plus a negative x squared, sort of cross them out when you get your 2x squared, so you know that you've done that subtraction and you don't accidentally subtract something twice or you don't miss anything. So hopefully those tips will help you be pro at doing operations with rational functions. And if you have any questions, as always, let us know.